Hi, my name is Manish Gupta, and in this video, I'm going to talk about flash attention, which is a very popular technique for efficient training for deep learning models these days. Let's get started. What is flash attention? Well, as you might already know, transformers are based on self-attention, and self-attention is quadratic in terms of sequence length. That has caused a lot of trouble in terms of doing training with very large sequence lengths. It requires a lot of compute power as well as a lot of RAM to do so, right? And causes a lot of latency, right? Now, several attempts have been made to solve this problem by actually having large sequence length. Several attempts have essentially tried to reduce the number of floating point operations. However, on in modern GPUs, compute speed has actually outpaced memory speed. And therefore, the bottleneck is actually memory speed rather than compute speed. Right? So to understand this, let's look at this pyramid. In this pyramid, what is shown is the memory hierarchy with bandwidth and memory sizes. Right? So at the bottom, you see CPU DRAM, which is available in plenty. So typically, you can have very large CPU DRAMs, but then the speed is super slow, 12.8 GB per second. As against that, the memory in GPU is of two kinds, high bandwidth memory or HBM, which is basically typically something like 40 GB and has a speed of 1.5 TB per second. Access speed is about 1.5 TB per second. Now, if you look at the really awesome memory, GPU SRAM memory, that is very, very rare. So, or rather very small in size, 20 MB only. However, the speeds are super high, 19 TB per second. This speed, as you can notice, is about an order larger, but then the quantity and the size is much, much smaller. Okay. Now, to exploit memory speed is what flash attention focuses on. Flash attention is an IO-aware exact attention algorithm. It's not an approximate attention computation, it's an exact attention computation that uses the popular tiling method to reduce the number of memory reads writes between GPU high bandwidth memory and GPU on-chip SRAM. So this one is essentially, high bandwidth memory. It is large in size, but then reading and writing to it multiple times actually reduces the overall speed and causes a lot of latency. So flash attention essentially uses styling to avoid that. The second thing flash attention does is to have fewer HBM excesses than standard attention, which is what helps overall improve the latency, reduce the latency. Right? Flash attention can also work with block sparse attention, and therefore it's also called as then its variant is called as block sparse flash attention. And this one is an approximate attention algorithm that is faster than any other existing approximate attention method as of now. Broadly, flash attention uses this concept of kernel fusion. So the idea is that a process in very crude terms inside a GPU is called a kernel. And then the idea is that if there are multiple operations that are applied to the same input, the kernel, the input can be loaded just once from HBM instead of multiple times for each operation. Okay, so essentially, if several of these kernels basically require access to the same input and they want to operate on it, you could load that input just once rather than each of those kernels essentially trying to load them, they load their own copies. And that's what is called as kernel fusion. Okay. So let's see how flash attention works in more detail. Before we get into more detail, let's see how a standard attention operation is done using the standard attention method shown in this algorithm. Okay, so recall that standard attention works like this. You have an input X coming in and you multiply by weight matrices so as to get QKV. And then you compute QK transpose that gives you S. You apply a softmax on S to get a matrix called P. Then, of course, you could also normalize, QK transpose by square root of D. But then for the simplicity, let's basically assume a non-normalized version where you get P. And then you essentially multiply P with V, the value matrix, so as to get the final output. Okay. Now, to be able to do any such computations, the matrices Q, K, V, P, O, everything has to be brought from HBM into SRAM. So all computations actually happen in SRAM. Okay. So therefore, the way the standard attention is going to be implemented is as follows. You have the matrices QKV stored in HBM. Okay, so the high bandwidth memory. You load Q and K. You can't load it over it entirely because Q and K are too large compared to the 20 MB SRAM memory that you have. So you load them block by block. So you load a block of K, you load a block of Q, and then you compute blockwise S, and you write that block of S to HBM. Now you of course compute these block by block, so the entire S gets computed in HBM. Then you read S from HBM again block by block, and then try to compute the softmax. So softmax on top of it so as to get P, and then this P is written to HBM. Now, finally, you load blocks of P and V from HBM to SRAM again, and then you compute O equal to PV and write O to HBM. That basically finishes off, that gives you your overall output, and that finishes off the attention computation. Now, this standard attention implementation, which requires several reads and writes to HBM. How can you avoid them is the question. Okay. So the main idea behind flash attention is exactly this, to avoid several reads and writes of the attention matrix to and from HBM. So you need to do two things to be able to do that. One, you want to compute the softmax reduction without access to the whole input, right? So essentially somehow you want to still read these block by block Q and K, but then you don't want to actually write those blocks to HBM and then read it again to compute P, and then you read it again to compute O. No, too many reads and writes, right? So to avoid that, you must be able to somehow compute partial softmaxes over only a block of Q and a block of K. Okay, that's the first step. The second step to make things faster and low memory intensive is to not store QK transpose at all. Okay. So you don't want to store QK transpose, although you actually need in standard attention implementation, you need QK transpose to be stored in HBM for the backward pass for gradient updates and so on, weight updates using gradients and so on, right? So, but then somehow there should be a way of handling QK transpose not to be computed entirely, but somehow still do the backward pass. Okay, so let's see how flash attention achieves this. So the first thing that flash attention does is tiling. It splits the input into blocks, which by the way, even the standard implementation of attention does. So you would split that into block. And then you're going to make several passes over input blocks, thus incrementally performing the softmax reduction. So you're going to do incremental computation of softmax computation. We will let's basically see how this is done. Okay. So this dotted box essentially shows you the entire QK transpose matrix, which is never computed, by the way, in flash attention. So what happens is that, so let's see what are the other things. There is Q, there is K transpose, and there is V, right? So those all exist. The green ones basically indicate that they are stored in HBM, the high bandwidth memory. Okay, remember the slow GPU memory. Okay, and the orange ones actually indicate SRAM. So what do? You basically run two for loops. I mean, in the first for loop, in the outer loop, so in the outer loop, you're going to actually load a block of K and a block of V. Remember, a block of K and a block of V. So outer loop essentially loops over a block of K and block of V. And then in the inner loop, you're basically going to load Q block by block. Okay. So you basically load the Q part, so for example, here I have first loaded the second block from K and second block from V, and then for every such Q and K, for every such K and V block, I'm going to load Q blocks one by one. Q blocks one by one. So for example, here I'm loading the fourth block, right? So essentially now these three blocks, Q, K, and V, in fact, K2, V2, and Q4 are actually in SRAM, right? So using these, you're going to do partial computation of the entire O. Okay, so essentially, remember, you're actually going to compute the entire O, not just the softmax QK transpose, but softmax QK transpose multiplied by V as well. And then this is what you're going to output to HBM. Okay. Now, for the next computation, next time you're basically going to load the next block because inner loop continues, right? So you're going to load the next Q block. And at that time, you are actually going to, you're going to, update your O that has been computed. So the overall output cannot be computed entirely until you have processed all the queries for a particular position. And therefore, but then this can be done incrementally. That's the best part of it. Okay. Now, to solve this entire mystery, what is important is to understand if softmax can be decomposed into smaller parts, into local aggregate. And can you do sort of aggregation over these local softmaxes? That's the overall point. Okay. Now let's try to understand how that is done. So to understand if I can compute local softmaxes and combine them to get the global softmax, let's look at this computation. Okay, how is softmax typically computed? Okay, so to recall, what is softmax operation? Well, softmax operation basically means that if you have three numbers A, B, C, what you want to do is to essentially compute EA, E raised to B, E raised to C, and then divide them by summation over EI, which is basically A, B, and basically summing over A, B, and C. Okay. Now, to make softmax more stable, what you do is the following. You, of course, essentially, you have x, and you take the maximum value of x, right? So that is m of x. We'll basically, so this vector is x, the input vector, and I'm going to denote m of x is the maximum value of x. And then what you compute is exactly this. So essentially, f of x is equal to e raised to x1 minus m of x. So rather than having just e raised to a or e raised to x1, I'm basically also going to have this minus m of x, so as to make it more stable, the operations more stable, right? Especially when the x values are very small. Okay. And then, of course, just like usual, I'll compute the sum. So I'll actually compute the sum over all of those f of x's. And then softmax is basically just f of x divided by the overall sum. So the overall sum is indicated by L. M is basically the max value, and then softmax is basically computed this way. Now, this is the standard softmax computation. No changes out here. When I have the full vector x, I can, of course, compute the overall max from the entire vector. I can also compute, the overall sum of all e raised to x's and overall sum of all of those f of xi's, right? And then it seems to be okay, right? However, when I'm doing this partial computations, I actually do not have access to the full vector, right? And therefore, I cannot compute this overall L in one go. So then what do I do is the question. So imagine that I break down my entire vector x into two parts, x1 and x2. Okay, and in general, I can break it down into 100 parts, or for that matter, as many blocks as I like. But then imagine that I break it down into two parts. Now, the idea is that, of course, I can actually compute the max for the first part, the max for the second part as well. And I can always say that the global max is going to be the max of both the maxes, right? So max operation in the data warehousing world, you can think of max operation as a distributive attribute, right? So if I have local maxes computed, I can compute the global max as a max of those local maxes. Now, the same can be told about f of x as well. So if you basically look at f of x, you can actually compute f of x partially like this for both x1 and x2 parts, both of them. And then you can actually take so this sum is essentially just a sum, right? So it's distributive. Sum is distributive by itself. Sum of local sums is the global sum, as simple as that. And that is how I can actually compute the global L using a combination of local Ls, Okay. And then that can be, of course, used so as to compute the softmax. So the nice point is that in the typical data warehousing terminology, M and L are both distributive in nature, and therefore the overall softmax operation is algebraic in nature. And that basically is the crux of the FlashAttention algorithm. Okay. In short, of course, you can look at the algorithm in detail in this paper, but in short, the way this works is as follows. Um, you first take the query matrix, key matrix, and value matrix. You tile it out in the sense you divide them into equal sized blocks. Okay. Now you're going to and you run an algorithm which has two for loops. In the outer loop, you're going to load a block of k and the block of v. So basically, the jth block of k and the jth block of v. And then in the inner loop, you're basically going to load the ith block of q. And then you're going to use all of them so as to compute, the local L, M, and then also the L and M basically, right? So that's what is computed in SRAM, and then this is updated. So of course, after you've computed these, you also compute O using the local operations, local V as well, V that you have loaded, right? So essentially, you compute O, and then you write out O, L, and I back to HBM. Okay. So you're not going to write out the entire QK transpose. QK transpose, remember, is very large, but O is actually much smaller, right? So you're essentially going to write out O, read and write O several times from HBM to SRAM. But then, since O, L, and M are much smaller compared to QK transpose, this is way more efficient. Okay. Now, the interesting part also is that they show in the paper that even for the backward pass, all you need is essentially these OIs, LIs, and MIs appropriately stored in HBM so as to do recomputation in SRAM for the backward pass. Yes, it actually includes some more recomputation to be done in the SRAM for the backward pass so as to get back your parts of your QK transpose that are really important for gradient computation. But then the nice part is that saving on the memory and saving on these reads and writes to HBM essentially help you offset for the extra computation that you need to do so as to compute your so as to recompute your QK transpose values from OI, LI, and MI in the backward pass. Okay, now that we've understood the crux of flash attention, let's understand how impactful it is. So here there are, what you see here are some numbers which compare the forward and backward, both passes combined runtime for GPT-2 medium model on an A100 GPU, right? So essentially, what you see here is that the standard edition involves 66.6 gigaflop operations, gigafloating point operations, right? However, flash attention involves more operations, and that is really required because for the backward pass, you're doing recomputations, right? You're doing recomputations. Well, that avoids storage of the large QK transpose matrix, and that's for it's very nice on your HBM memory. Okay. Now, if you look at HBM read writes, well, a lot of read writes need to happen, 40.3 GB, right? However, in case of flash attention, it's just 4.4 GB, which basically means that you can actually now enable much larger sequence lengths, right? Runtime wise, standard attention just takes about 41.7 milliseconds. However, flash attention takes only 7.3 milliseconds. So that's the beauty of flash attention, right? Also, if you look at the block sizes, now flash attention depends on blocks. So essentially how many blocks you divide your key matrix, value matrix, and the query matrix into. So as you increase the block size, what you observe is that the number of HBM accesses reduce. That's obvious. However, what you also notice is that there is a sweet spot where the number of the amount of the runtime does not really decrease by much. So at about 256 block size, you can say that, hey, I'm done. I don't, it's not really helping me reduce my runtime more. Okay. Now, as I mentioned earlier, this kind of dense flash attention can also be applied to computations where your attention matrix is sparse in nature. Right. So essentially, techniques like BERT have essentially explored these sparse attention computation methods. Now, for block sparse flash attention, what you observe is that in this plot, what is shown is the following. So sparse attention basically means that if you really were to compute the entire QK transpose, some of those blocks are going to be empty. So they are going to be zero. And therefore, in case of flash attention, what you could do is to just not compute those blocks. It's as simple as that, right? So what you observe is that while dense flash attention, so on the x-axis, you observe the non-zero blocks, how many non-zero blocks exist in the sparse world. And then on the y-axis, of course, we plot latency. So what you observe is that the dense flash attention, of course, is uniform. It basically takes quite some time. But then the block sparse flash attention actually, has lower latency, linearly less compared to the number of non-zero blocks. Basically saying that the block sparse attention, the block sparse flash attention can totally exploit sparsity and can actually reduce to much lower latency proportional to the amount of sparsity in your attention matrix. Okay, so now people experimented with the BERT model. People also experimented with standard transformer and then with GPT-2. And what are the observations? Well, the observations basically show that compared to the best implementation of the BERT model, the NVIDIA MLPerf implementation, flash attention basically saves 15% on the wall clock time. This is a BERT large model, right? On GPT-2 small model, flash attention basically leads to 3.5x speed up on when trained on open web text for language modeling task. And if you compare the perplexity, the quality of the model is perfect. It's exactly the same, right? Because flash attention is not approximate, it's doing the exact computations, but then you basically can do it 3.5x speed, right? With GPT-2 medium, this speed is about 3x. So, and again, as you notice, the perplexity does not really change much because you're doing just the exact computations as is. Now here are results shown on long range in arena benchmark datasets. Several datasets, as you see them here, the quality, as you see, does not drop much as you go from transformer to flash attention to block sparse flash attention. Remember, flash attention is exact, but block sparse flash attention is inexact, right? It's an approximation. Still, you observe that the quality, that the accuracy metrics across different datasets are more or less the same. However, if you look at it, there is a 2.8x speed up. Now, the sizes of these sequence lengths is pretty good, pretty high. So for example, in long range arena, it's called long range arena because the max sequence length can go up to 4,000, right? So therefore, it leads to a really awesome speed up of about 2.5x, 2.8x. Now, let me also talk about what can you get because, what other benefits you can get because of flash attention. Now, since flash attention saves on memory as well, you can actually now afford to have a larger max sequence lengths. So what happens then? So if you basically compare with the Megatron LM's GPT-2 small model with the 1K context length, and then you can now run 4,000 context length with flash attention, what you observe is that, of course, you get about 1.3x speed up, but that's not what is important. What is important is that you actually get much lower perplexity. So flash attention can actually enable longer context in transformers, leading to higher quality models, 0.7 better perplexity on GPT-2 small model with the open web text corpora. Uh, the authors also measured the results on two document classification tasks where the input documents are pretty long in size. So the average length of documents in these two data sets is a few tens of thousands of tokens. And so yes, so basically, for example, on 16,000 max sequence length, you observe that the accuracy that you obtain, classification accuracy, is several points larger than the accuracy that you can obtain with 512 as the max sequence length. Similarly, on the other data set, you observe similar gains, much better accuracy, with very large 16K kind of max sequence lengths compared to just a max sequence length of 512. Now, there's yet another complex task called as PathX challenge. Now, in this challenge, the idea is that you're given an image, a black and white image, and you have to figure out between 2 points if there is connectivity or not. Point-wise information, pixel-wise information is passed as a sequence in a rasterized form to a transform model. Now, what you observe is that various different transform methods have been tried out, and on PathX and Path 256 challenges, both of them, no transform method has been able to ever get accuracy better than chance, right? However, the flash attention and block sparse flash attention are the first models to get, which are able to get better than chance performance on these PathX and Path 256 challenges. So you can actually get an accuracy of 61.4 and 63.1, which none of the earlier transform models could achieve. This is all thanks to the high max sequence lengths that this model could basically incorporate. Now, here is a comparison of flash attention with other forms of attention that have been proposed. For example, PyTorch attention, Megatron attention, Linformer attention, OpenAI sparse attention, these four different methods. So on the left plot basically shows you runtime, the right plot shows you memory footprint. So what you observe is that for max sequence lengths less than 512, flash attention is both faster as well as more memory efficient than any other existing attention method. So flash attention is this dotted black line, as you see, right? What you also observe is that for a sequence length greater than 1K, there are these two crossover points where some approximate methods like attention methods like Linformer actually become better than flash attention. However, in terms of runtime, however, flash attention is still always better in terms of memory usage compared to any other existing attention methods. However, if you basically just compare in the approximate attention world, what you observe is that the block sparse flash attention, which is an approximate attention method, is actually the best, both in terms of runtime as well as in terms of memory. Okay, so in summary, in this video, I talked about flash attention, which is an IO-aware exact attention method. I also broadly talked about block sparse flash attention, which is essentially an inexact approximate attention computation method. These methods essentially, the way they become super fast is by actually reducing HBM, the high bandwidth memory access, and try to do most of the things in SRAM. Right? It avoids storage of the QK transpose matrix, and the way it makes up for it in the backward pass is by doing recomputations. The main crux of the overall algorithm is that softmax is an algebraic operation, which can be expressed in terms of L and M, as we saw in this video. right, which are both distributive in nature, the max and the exponential sums, which are both distributive in nature. That helps softmax to be an algebraic operation, and that is what enables the entire flash attention algorithm, right? In the paper, the authors have further shown in the appendix specifically that the flash attention is actually applicable to several scenarios, several variants or more general variants of attention computation, like normalization. So yes, we only looked at the QK transpose, but also works when you have square root of d as the normalization factor, which is mentioned here, right? It is also applicable for various kinds of masking. We already talked about the block sparse matrices where blocks are masked out. So essentially, so even if you have some sort of masks, flash attention works nicely even in those cases. It also works when you have dropouts. So essentially, if you have certain computations which are going to be ignored, right? Flash attention, the algorithm can be very easily modified to incorporate them as well. We also saw several empirical gains across BERT, GPT2, and Transformer models. As future work, this is a very interesting paradigm, and as future, it will be nice to see how the authors can actually include these flat attention kind of modules right into CUDA, right? So that it can compile with CUDA, and then programmers will have much simple time, less harder time actually trying to implement flash attention for their architectures, right? Of course, this was just one IO-aware deep learning mechanism. Attention is not the only IO-aware, IO-intensive task that happens in deep learning, right? There's several other IO-intensive tasks that happen in deep learning computations. Many of them can actually benefit from these flash attention kind of modules. Lastly, this algorithm was proposed mainly for a single GPU computation. Now, if you have multiple GPU computation being done for attention, and this is sharded computation in that sense, then you have to be also careful about the inter-GPU talk, right? So communication across GPUs. Now, extending this algorithm to actually incorporate a new factor of this inter-GPU communication latency is going to be fun. Okay, so that's all future work. If you want to try out flash attention, the code is right there. That's it. That's it for this video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.